So what if we could teach a machine to actually imagine? I mean, to look at the world around it, figure out the rules on its own, and predict what's going to happen next, just by watching. It sounds like something out of a movie, but let's dive into how this is becoming a reality.
And note, this isn't science fiction. This is the whole quest for what AI researchers call world models. These are AI systems that build their own internal understanding of their environment. By getting a feel for cause and effect, the basic physics of their world, they can plan their next move entirely inside their own imagination.
That right there is the million-dollar question. How do you actually get a robot to learn this? How do you build one of these things effectively? Especially when its only teacher is just a stream of pixels. No one's feeding it the laws of physics. It has to figure it all out from scratch.
Well, as you can probably guess, it is incredibly difficult. Because when you try to train these models, you almost always run into this massive problem, a really frustrating failure mode that researchers call representation collapse.
And collapse is, well, exactly what it sounds like. The AI basically finds the laziest possible shortcut to solve its task, which means it learns absolutely nothing. It starts mapping everything it sees, a block over here, the robot arm moving, a block over there, to the exact same internal idea. It essentially just gives up and goes blind, making its model of the world totally useless.
The researchers have the perfect analogy for this. It's like a student who realizes that if they just answer, "I don't know," to every single question, they can never technically be wrong. It's a clever, lazy shortcut that completely defeats the whole point of learning in the first place. And this right here, this is what that lazy collapse actually looks like from the AI's perspective. Its imagination just turns into a total blur. It can't tell the difference between any two moments in time, so its predictions are completely meaningless. For a long, long time, just preventing this has been the central challenge for the entire field.
But a new paper is introducing a hero to our story, a model that really elegantly solves this problem. It's called LeWorldModel, or LWM for short, and it's built from the ground up specifically to be stable and to avoid this collapse.
So what makes this LeWorldModel so promising? Well, it's this awesome combination of features. Not only is it stable and reliable, but it learns everything directly from pixels. It's also super simple with just two main goals. And maybe the best part, it's incredibly efficient. We're talking about training it on a single regular gaming GPU in just a few hours. That's a huge deal for making this kind of research accessible to way more people.
So, what's the secret sauce? How does it actually pull this off and avoid that lazy student problem? Well, the answer lies in this beautifully simple, two-part recipe for learning.
Okay, the recipe has two key ingredients. Step one is pretty straightforward. The model's main goal is to predict what its own internal idea of the world will look like in the very next moment. That's its job. But step two, this is where the magic happens. It has a special rule that forces its internal ideas to be diverse, which actively stops it from ever taking that lazy shortcut.
Right, so how in the world do you enforce diversity on an AI? You can't just tell it, don't be lazy. Well, LeWorldModel's incredibly clever trick is to basically tell the AI that the entire collection of all its possible internal ideas about the world has to conform to a very specific mathematical shape.
And that required shape is a perfect bell curve, or what mathematicians would call a Gaussian distribution. So instead of letting all its ideas collapse into one useless, blurry point, the model is forced to spread them out to fit this exact pattern. This gives it a mathematical guarantee that its internal map of the world is always going to be rich and varied. Problem solved.
Okay, a simple, elegant theory is one thing. That's great. But the real question is, does this recipe actually work in practice? Well, let's take a look at the results, because they are pretty staggering. Let's start with a big number. 48 times. When it comes to planning ahead, which is the entire point of having a world model, LeWorldModel can be up to 48 times faster than other, much larger and more complex models.
And to put that number into perspective for you, a competing model, DynoWM, takes around 47 seconds to plan out a series of actions. LeWorldModel does it in less than 1 second. I mean, that's the difference between a system that can only work in a lab and one that could actually operate in real time. And the advantages just keep stacking up. See, unlike other models that need pre-trained pieces or rely on fiddling with 6 or more different settings, LeWorldModel learns everything end-to-end, has just one main dial to tune, and, get this, it has that provable mathematical guarantee against collapse. It's just simpler, way more reliable, and a lot more flexible.
But honestly, this is the result that just makes you stop and stare. On the left, you're seeing a real robot pushing a block. On the right, that's what LeWorldModel imagined would happen, given the exact same start and the same actions. The alignment is it's stunning. It learned the physics of its little world so well that its imagination is almost indistinguishable from reality.
And this is where it gets even more interesting. Because the model has such a good grip on reality, the researchers realized they could actually test its physical intuition. In other words, does it actually know when the laws of physics are being broken? So they ran this fantastic experiment. They measured the model's surprise, which is really just a fancy way of saying its prediction error. When an object just changed color, which is a visual change, not a physical one, the model was like, okay, whatever, not very surprised. But when an object suddenly teleported across the screen, a physically impossible event, its surprise level shot through the roof. It learned, just from watching pixels, that things in the real world just aren't supposed to do that.
So, let's zoom out here for a second. A smarter, faster, simpler world model, why is this such a big deal? What does this all actually mean for the future of AI and robotics?
It really matters for 3 huge reasons. First, because you can train it on a single GPU, it completely democratizes this research. It lets way more people experiment and innovate. Second, its insane speed makes real-time control for robots that can think on their feet, a much more achievable goal. And finally, by giving everyone a simple, stable foundation to work with, it lets the entire field stop fighting with these basic training problems and start building even more capable, more intelligent systems right on top of it.
And that really leaves us with this one final, fascinating question to chew on. LeWorldModel proves that an AI can develop a real, intuitive grasp of physics just by observing the world. So, if it can understand cause and effect on this level today, what other, much more abstract concepts will it start to understand tomorrow?